Okay, here we have a case where a first order system, shown here, where the elevated deflection, rate of elevated deflection, is proportional to the elevated deflection itself. If you take the LaPlace of that system, the LPT, you'll get this here. And we can neglect initial conditions for the transfer function. So if we take the output over the input, the elevator over the elevator command, here's the elevator output, and here's the elevator command, that ratio from this equation over here is going to give me A over S plus A, and we call that a first order system. First order. Now, if the input, the commanded input, is going to be a step, then we can replace it with 1 over S. And then that's going to give us our output, elevator, is equal to 1 over S, which is the input, times A over S plus A. And if we want to find the inverse Laplace, the step response, we just have to take the inverse Laplace of this system, which we'll do using partial fraction expansion, or what we call PFE. So this first step is the LPT, takes the LaPlace transform of this LPT, and the second step is the PFE, the partial fraction expansion. So the first step in our partial fraction expansion is to take our transfer function and divide it into two terms, one term for each term in the denominator. So I'll have a constant A0 over S and a constant A1 over S plus A. And if I knew those constants, I could get the inverse Laplace transform almost by inspection by just looking at the inverse Laplace transform of these two terms. So here's a simple way to find these terms almost by inspection. If you are trying to find A0, then notice that if you multiply every term by S, you'll isolate the A0 by itself. So if I multiply every term by S, the S will cancel here, and I'll get S. Now this equation holds for all values of S. So just pick S equals 0. So if I pick S equals 0, since this is already canceled, these S's have canceled, then I'll get A0 equal to the constant A, capital A, over little a, as I let this S here go to 0. And that's how you'd find capital A0. Similarly, if you were looking for A1, now you would multiply every term by S plus A. So when I multiply the original transfer function by S plus A, the S plus A's would cancel. I multiply the A0 by S plus A, and I multiply the A1 term by S plus A, and that's going to cancel this term in the bottom, isolating A1. Then let S equal minus A. When I let S equals minus A, this A0 term is going to be isolated. And if S equals minus A over here, then I have A1 equal to minus A over little a, since S equals minus A. And that's how I find my two constants. Then if I substitute A0, with capital A over little a, and A1 with minus capital A over little a, then I have this transfer function shown at the top, which I can see by inspection the inverse Laplace. The inverse Laplace is going to be simply capital A over A, a constant term. And then the inverse Laplace of this is going to be minus capital A over little a, e to the minus at. You have to memorize the inverse Laplace for a first order system. That's the only one you really need to memorize other than the symbol values of S. Therefore, the inverse Laplace of the transfer function, using the relationship we just developed over here, is going to be equal to capital A over little a times 1 minus e to the minus a t. And if you were to plot this function, you would get a first order response like so, with a steady state value equal to capital A over little a, and a time constant where it reached 63% of its final value at 1 over a. So the time constant is equal to 1 over little a. And that's how you pick the performance metrics for your system.